Okay, so welcome back, everyone. We are ready to start our Monday afternoon session. The first speaker is Michael Wondrak from University of Frankfurt, and he will tell us about far from equilibrium shear transport from strongly time-dependent spacetime. Please, Michael.
Thank you very much for the nice introduction and for the nice organization of that conference. I already enjoyed the morning session, and I'm quite happy that we have already learned something about hydrodynamics, so that I can skip a little bit of my talk and come a little bit more to the results. Great. So the focus should be on far from equilibrium physics. So what is that? What we see here is a phase diagram of some kind of substance. In this case, the substance of QCD, and in particular, there's this phase of the quark-gluon plasma, which is investigated in heavy ion collisions. And the two axes that we see is the baryochemical potential and the temperature. But this system is only valid in equilibrium. So actually, what happens if we are out of equilibrium? So if there are some gradients. And this is what we want to investigate. Okay, far from equilibrium physics is a rich subject, and holography offers the possibility to explore this regime, namely the possibility to study real-time dynamics or strongly coupled non-dilute systems, which is very difficult to track otherwise. And there are different applications. First of all, simply from theoretical side, that you can study how thermalization of a system, of a field theory state works. What are the patterns? Is there a top-down or bottom-up thermalization? Furthermore, it is relevant for condensed matter systems. For example, if you have a quench in some parameter and want to study how the system behaves afterwards. And as already indicated, it is relevant to the quark-gluon plasma and there to the formation and thermalization. And this is the example that I want to go on with this talk. So the quark-gluon plasma is believed to be present in the early phase of the universe. So here you have two graphs. One is the history of the universe from the Big Bang, and then when the system expanded and cooled down. And right there in the beginning, there was the quark-gluon plasma phase. On the other panel, you see how we can produce the quark-gluon plasma on Earth in the lab, namely by mini Big Bangs in heavy ion collisions. So again, we have a timeline on the x-axis. So the system starts out with two Lorentz contracted nuclei that pass through each other and interact. And by that, they produce a very highly excited state that expands. At some point, it can be described by ordinary hydrodynamics. The quarks and gluons, which are deconfined, then do particleize, so they become particles. And then everything starts out to decouple, and finally there's a free streaming phase. And after a time of 10 to 15 Fermi, so femtometers over the speed of light, we find trajectories in the detector. But what you can see in this picture quite nicely is that there is a gap in the beginning. So a gap where the system is very far from equilibrium, and this is the gap that we want to address. We want to look especially for the system's shear transport in such a dynamic, hot and dense, strongly coupled situation. Okay. How do we do that? So in the beginning, what is quite easy to see is if those two nuclei collide, they have to transfer energy from kinetic energy into thermal energy. So the most important effect is the heating up. Is there already a question? It doesn't seem to be the case. Okay, I continue. If there's some question, please don't hesitate to ask. Yes, so we want to study what is this heating up or the energy deposition effect on shear transport. And below you find a sketch of how we treat that holographically. So we have our typical system. This is our field theory living on the boundary. And then we have the radial direction with the black brane. And starting from an equilibrium situation, we have a period of energy deposition, so mass infall in our spacetime, and then we end up in an equilibrium situation again. During that mass infall, the horizon position changes, and on our field theory, we have introduced strong temporal gradients, and therefore the system is far from equilibrium. So far, so good. This is the upshot. And so let's talk a little bit more about what we're going to see. So first, we will do some preparations from hydrodynamic and how you calculate eta over S in equilibrium. So the famous Kofton-Son-Steinitz and Polycastro-Son-Steinitz calculation. And then we will combine that with a far from equilibrium setup that we have already sketched. And then we will combine those to define shear transport and shear viscosity far from equilibrium. And finally, we will look for applications in heavy ion collisions. Okay, so as we have learned already this morning, hydrodynamics is a very versatile theory and also applicable to condensed matter systems. There was some electron hydrodynamics. So just to say the most important things, it is a set of coupled equations. It is the conservation equations plus some constitutive relations that relate the microscopic and the macroscopic objects. And it is closed by the equation of state. Typically, it is thought to be applicable only for long wavelengths, but there is new development that hydrodynamics is also applicable far from equilibrium, out of equilibrium. And this has to do with the convergence radius and looking for hydrodynamic modes. And I've listed some of the recent developments in that field. And we can talk to that a little bit afterwards. This also gives the motivation for our study that we apply hydrodynamics and talk about the shear viscosity in that regime. Okay, so where does the microscopic theory enter the game? It does by the definition of transport coefficients. So what we see here is the constitutive relation, namely the one for the energy momentum tensor. And there are two components. In principle, you have an ideal component and then non-ideal corrections. So the ideal one has to do with the energy density and the pressure, while the non-ideal components are then derivative corrections to that. At the first order derivative, we encounter in general a shear viscosity and a bulk viscosity. In principle, there are different ways and consistency relations among different transport coefficients. Okay. In our case, we study superconformal field theory, and this is our holographic dual to our bulk spacetime. That determines what the transport coefficients are. To give some intuition for the shear viscosity, let's look how it acts. So let's look for that sketch that we have below. So we have two planes, and the upper plane is moved. And we see that there is a laminar flow in between those two plates, and the velocity profile has a linear shape in this ideal case. This the slope of this profile gives us the shear viscosity. So it is the efficiency, how good transverse momentum, and in that direction, is diffused perpendicular to that. And what we can also see quite nicely, so the ratio of the force over the area has to do with the xy component of the energy momentum tensor. So eta is our proportionality constant, and then we have this gradient. What we want to keep in mind is that we have to look for the xy component of our energy momentum tensor and also of our metric if we want to calculate the shear viscosity. Okay, near equilibrium. From the holographic perspective, this can be easily, now it's easy to see, calculated and was first done in this Polycastro-Son-Steinitz paper. So what was introduced, there was a gravitational fluctuation in the spacetime, namely an xy component, and then the linearized Einstein equations were considered. And there's a relation that brings you from a retarded Green's function two transport coefficients, and this goes under the name of Kubo formula. But first, if we have a metric fluctuation in our spacetime, we can do the boundary expansion of this object, and then we find as a subleading term the vacuum expectation value of our object, of our boundary operator. And from there, we can also find a two-point function, namely the retarded Green's function. And using the Kubo formula, we take the retarded Green's function to obtain the shear viscosity. Below, we see a plot on how this Kubo formula works, if you want to. So we have the limit omega to 0, and this is explicitly done in this numeric calculation here. So we have omega, and we look for the imaginary part of the retarded Green's function over the frequency, and we find that we asymptote to very nicely to that value, which is given in orange, and which is the value 1/4 pi. Great. By the way, why do we state eta over s and not only eta? Well, by normalization to s, we first of all get rid of dimensions, and secondly, we talk about the degrees of freedom. So actually, eta over s is some quantity for entropy production per degree of freedom that we see in this context. Okay, what does this has to do with our real world? It was shown in a later paper with Kovtun that holographic systems generically give a value of 1/4 pi. There are exceptions where smaller values are possible. For example, if there are anisotropies, or if you introduce corrections where you have a finite number, finite gauge rank, or the Toft coupling is reduced. But in principle, 1/4 pi is a good order of magnitude. If you look for this plot below, we have eta over s, so the shear viscosity to entropy density ratio, as a function of temperature. What we have seen up to now is that the holographic value, as it is here, is temperature independent, and again, it is the orange curve. While there are two other results displayed in this figure, namely some from QCD calculations. One is from lattice QCD. These are the small green dots that you can see here. The others are from the functional renormalization group approach, and the fitting curve is the black one that you find here. So what we see is that this value 1/4 pi is of a good order of magnitude estimation, and that it is close to what you expect from a fundamental, or more or less a priori ab initio calculation from QCD. So far, so good. We have talked about eta over s near equilibrium. But what happens far from equilibrium? First of all, I want to introduce the setup that we are working. So our far from equilibrium model. As motivated in the beginning, we look for a system which undergoes a sudden energy deposition. So, and furthermore, we want to have a finite chemical potential. So to look for what is the baryon chemical potential doing in our setup. Holographically, this is displayed by an Einstein-Maxwell theory. So you have the ordinary Einstein term plus the Maxwell term plus some meta part. And we will use the meta part for an explicit configuration. Namely, we are interested in a Vaidya system. So a Vaidya system is one where we have null matter, so some pressureless dust is the geometric interpretation, and that falls onto your black brain with the speed of light. So what you reach by that is a concentrated matter infall, which has just the shortest amount of time that it is in the system, and where you can choose the profile of how much matter comes in which time span is really to choose. So especially we have two free functions. We have the mass parameter of the black brain and the charge parameter. The metric is fairly easy. If you look for the blackening factor, it looks like Reisner-Nordström in ADS asymptotics, but with the mass and the charge now time dependent, so V dependent functions. So we are in adding Finkelstein coordinates, and this V corresponds to an ordinary time t on the field theory side. For our calculations, we will explicitly use a Tunch profile, so a temperature increase with a characteristic timescale delta t. Okay. So how do we combine those two objects? So E/s and far from equilibrium. And we have two obstacles to overcome. First of all, in E/s, there is the entropy density S, which is a thermodynamic quantity. But if we go far from equilibrium, we have to generalize the definition of what is entropy. And second, we no longer have time translation invariance of our system. So that work that we had done before, where we had the retarded Green's function in frequency or in momentum space, is no longer possible because we cannot simply do a Fourier transformation. So we have to come up with a more clever idea of how to go to the frequency space. Okay, so starting with the thermodynamic part, this is the typical identification. We have the Hawking temperature of the black brane, which equals the temperature of our field theory state. The entropy density of the black brane transforms to the field theory side, and also the U1 gauge field that we have gives the chemical potential. This is in equilibrium. If we go out of equilibrium, we still can use holography to have direct access to the energy density and to the pressure. Now we can use the equation of state and say that this is our fundamental quantity, also valid out of equilibrium. So we know that the pressure is already the generating functional of connected diagrams if you are in the field theory setting. And then we can do ordinary derivatives. So we take this equation of state, we derive the formula for our temperature and for our entropy density. And then we use the time-dependent quantities of epsilon and p to get time-dependent quantities, temperature and entropy density. This is how we define our S in the far from equilibrium regime. Now coming to our shear viscosity. So the goal is still to achieve some frequency space formulation. And we will find time-dependent frequency Fourier transformation to go there. But first of all, we have to find out how to get this retarded Green's function. So we start out with a similar consideration as in the Fourier-Castro-Stein case. So we look for a metric fluctuation for hxy. And we solve that equation along the lines of Chesler and Yaffe. So we use a method of lines. We have a pseudospectral method for each time slice on the radial direction. And then we do a time forwarding with Rummelkutter fourth order scheme. Okay, so we do that. And as we know from holography, very basically, is that the subleading term in the boundary expansion gives us the 1-point function of our operator in the field theory set. A 1-point operator, a 1-point function is not yet a 2-point function like the retarded Green's function, but we can do a clever trick. We can apply the concept of linear response theory. So linear response theory tells us if you have some source, you can fold it with the retarded Green's function, and then you find out what your quantity looks like. So now if we take our source to be very localized, this integral actually collapses. And we only have the retarded Green's function left over. So using this trick of a localized source, we can use the 1-point function that we can calculate and induce from that our retarded Green's function. That is quite nice. But still, this retarded Green's function depends on 2 times and not 1 time and 1 frequency. So what do? We reorder the time that we have. We introduce an average time and we introduce a relative time. And we do the Fourier transformation with respect to the relative time. This goes under the name of Wigner transformation and is from time frequency analysis something that is quite often used, but not too often yet in holography. So this is what we used here. And so we have a Fourier transformation with respect to relative time, which is dependent on a reference time, namely our average time. So far, so good. And using this concept on our 2 times Green's function, we can derive the retarded Green's function with a frequency notion. So let's see how that looks in practice. So here again, we have our trick. The 1-point function gives the 2-point function. Let's look for the left-hand side plot. This is a sketch of our spacetime. So we have the radial direction with the boundary and the horizon position. And here the time, the x-axis is the time evolution. Do not worry why the horizon does not change. This is simply scaled to be 1 for all times, even though there's a mass infall at time ts. Great. So what do we do now? We introduce at the boundary a localized source. So not really a Dirac delta, because that is numerically hard, but a very peaked Gaussian. And we look how our metric fluctuation evolves in spacetime after we have introduced that fluctuation. The right-hand side plot shows how it behaves, namely the subleading term, which is then proportional to our 1-point function txy. And you see some ring down behavior as expected. And you see 2 quite nice things. First of all, you note that the period before time 0 is longer than afterwards, actually by a factor of 2. And you also find that the envelope that you have here is twice not as steep as the envelope that you have here. So this means that if we look here at the dominant quasi-normal mode, this actually scales with temperature, the real and the imaginary part of the quasi-normal mode. And the factor of 2 actually is related to the mass that we have thrown into our black hole solution. We are not forced to only look for one pulse, but actually we can introduce the pulses at several times. So a blue, a purple, and a red one. And all of the times we look for this ring down behavior. Reordering now these 2-point functions in time space, we are able to apply our Kubo formula to do the Wigner transformation, apply the Kubo formula, and end up with a time-dependent shear viscosity. So this brings us to the results. Okay, what you find here is some study for parameters relevant to this heat up phase at RHIC collisions, so the relativistic heavy ion collider in Brookhaven. So below you have the temperature profile. Temperature is a function of time, and there's a blue and an orange one. In the upper panel, you find the corresponding value of eta over s. So let's start with the orange profile. This is a temperature doubling within 0.6 Fermi. And the reaction of eta over s is a dip that is already going to about 40% of the equilibrium value, and then approaches the equilibrium value again. If we now decrease our heat up time scale, namely to 0.25 Fermi, we see that the minimum is lower, that it is more pronounced, and actually there's also an overshoot in the system. So that means that there's quite some interesting dynamics. And overall, it is fascinating to see that we have already reached 60% of the equilibrium value at this point. So now let's study further configurations and also include the situation at the LHC, so where you have higher temperatures.
Can I ask something?
Yes, please.
Michael, so if you make your pulse, if you tweak your pulse to make it like narrow and narrow, so you put more and more energy in the system, can you push this non-equilibrium eta over s below 0?
That's a good question. We have stick to the rules, the parameter regime for the heavy ion colliders. I have some intuition that we do not go too low with that plot that you see at the moment. But that's an interesting question.
Yeah, you know, I mean, in a sense, this non-equilibrium eta over s that you use is, in a sense, a resummation of all kinds of higher order contributions to hydrodynamics. And I'm not sure whether the typical unitary arguments still hold that this should be positive. Yeah, that I'm not sure about right now. But it's okay if you, yeah.
Yes, so if you look for resumed arguments, we will come to that in just 2 slides. You find also drops, so from effective kinetic theory and also from other ideas from holography.
Okay.
No study up to now that I have seen in literature gives you a value of e⁻s smaller than 0. This is actually interesting to see. We have to note that we have this Wigner transformation, and so you also have a little bit of information transfer from the future to that time that we are at. But yeah, so that remains speculation on my side how that goes, but it's an interesting question and definitely worth to proceed to look what happens.
Okay, thanks.
Great. Yes, so coming back to this plot, now we have e⁻s as a function of temperature, and also included a temperature increase by a factor of 10, which can happen at central LHC collisions. The shaded region.
Sorry, may I interject?
Yes, please.
Just on the previous question, you did define your shear viscosity through the imaginary part of a retarded Green function, right?
Yes.
So then the usual positivity of dissipation argument should apply, even though this is non-equilibrium.
Okay. That sounds interesting.
All right, thanks, Blaise.
Maybe we can discuss this afterwards, but that sounds cool. Okay, so far so good. Yeah, we have the shaded regions, which simply are the limits on our time range. So from 0.25 to 0.6 Fermi. The shorter is this time scale, the more pronounced the curves are. And the different colors represent the different temperature increases. What we find is that all these curves demonstrate a minimum around 1.3 critical temperature, which is quite remarkably. And we also see that the lower curves asymptote this red curve over here. So it seems that the temperature increase is not the most dominant factor for the decrease in e⁻s, but it is the time scale. So this heat up time scale, which is the more dominant parameter. Great. So let's come to some comparison. So first of all, here we present some updated values from FRG and lattice QCD. So it's a little bit similar to the situation that we have looked in the plot before. It is still the near equilibrium calculation that they do. In blue is the curve from Polycastros on Starinets, and this is the regime that we enter. So what we find is that the far from equilibrium effect brings you relevantly lower than what you expect in near equilibrium situations. But we are still of the same order of magnitude as what you have in those models from QCD. And then coming back to the question, at least a bit, you find a reduction in e⁻s far from equilibrium, also from other approaches. So I've given some of those references. For example, if you have anisotropies, or if you do that resummation as done in RHIC, there's also a paper by Lublinsky where one could look at. Yes, and there's also some funny thing. There's some rheological behavior of fluids where the history of a fluid also takes a role. And this is discussed in this paper by Bechtasch et al. From effective kinetic theory side. So let's conclude. We have looked for e⁻s, a holographic calculation far from equilibrium, where the strong time dependence effect is what we presented. And we found strong deviations in the equilibrium value, namely by 60% downwards or 10% upwards, which is relevant at least for RHIC and LHC. This has an impact if you do simulations. And then in return, also for the extraction of the shear viscosity if you look for experimental data. And the calculation procedure as we have presented it here is open to other transport coefficients as well. So it is not limited to e⁻s, but it could be readily used for other objects. So thank you for your attention, and I'm here for questions.
Thanks, Michael, for the nice talk. So questions, we have 15 minutes for questions. Let's go.
Yeah, a question for me. Can you just shortly repeat what is the difference in the definition of these out of equilibrium, for example, entropy density versus the equilibrium definition? If I understood correctly, you kind of took the same definition, right? Just for the time-dependent background, or what was the key difference?
If you go out of equilibrium, you have to be careful what is the equation that you use from your equilibrium system and prolong it to the non-equilibrium case. So which is the formula where you replace your ordinary quantities by time-dependent quantities? You could also take the temperature formula that you have already derived, for the temperature, you use the derivative of the blackening factor. And after evaluating this quantity, you then replace your mass function to be a time-dependent mass function or whatever. But we found that this is inconsistent also for the entropy density to have a little dip. So the way that we go is exactly like equilibrium, but one special case of the equilibrium case, namely using the generating functional and then trying to be most general in there, going to bulk quantities and then replacing the bulk quantities. I can show you also some different definitions if my computer helps. So here you find different definitions of temperature as a function of time. For example, if you take simply if you evaluate the Hawking formula with this f prime, you have this blue curve where you have first a dip, and then you end up with the new equilibrium configuration. You can also try to use the formula from surface gravity, so one step more general, but then you encounter an increasement, which seems to be unphysical. But if you go for the generating functional directly, you have this green curve, which looks, at least from looking for monotonicity, the most reasonable.
More questions?
Hi, maybe just a comment. You could also argue that the generating functional is the most fundamental object in the context of quantum field theory.
Yes.
Anything else?
So then I would have a question to Blaise about his comment, if we start from the imaginary part of the retarded Green's function, that this ensures that eta over s is larger than 0. So if I may reverse the order of questions.
Looks like Blaise disappeared.
Might happen.
Yeah.
Great. So if you have some questions later, I'm still available via email, and there you can find it, and also the references.
I could speculate on what Blaise maybe meant, since we have a minute or so. Usually you derive the bounds on the, or that's one way to derive bounds on transport coefficients, like the positivity or non-negativity of the shear viscosity. You can derive that also from unitarity conditions on the Green's functions. And I think that was also what René asked about, and I think that was also what Blaise commented on. I think that the general statements should still apply, but probably we should discuss a bit more what happens in these time-dependent cases when you have no time translation invariance, and if there's anything subtle there when you do the Wigner transform and such.
Yes.
I don't know the answer.
Yeah, very interesting question, Barini.
Any other comment?
Maybe you didn't notice that Bless asked you to repeat the question saying he was on the train, so on the chat. So maybe you can chat with him.
Okay, thank you.
I'm just reading the chat.
Oh, I'm afraid I don't have access to the chat, at least in this presentation mode.
In Zoom, you always have access, but depending on the version, can be more complicated.
Okay.
Anyway, you can talk to him. I just.
Well, I can read his statement. He wrote that I meant that generally omega times imaginary part of the retarded Green's function needs to be positive for causality, but indeed one should check carefully the assumptions, if any, behind this statement. Thanks, Blaise, if you can hear us.
Any other comments? Okay, if not, let's thank Michael again for the nice talk and let's move on. Okay.
Ah, now I see the chat.
Okay, Marcus, are you around? Yeah, I see you.
I am here. Can you hear me?
Yeah.
Good. I can hear you too.
Okay.
Sorry.
Yeah, try to share your slides.
Sure. I will share my screen soon. Let's see here. For some reason, my background was not working. Okay, good. Okay, let's see here. Good, check. Good. Good.
I see you. Okay.
Check. All right. Can you see my screen?
Yeah, that looks good.
And I will.
Full screen maybe or something like that.
Correct. Okay, so I will begin right now.
Yeah, that looks good. So let's just wait for the correct time. We have 7 minutes. And then I'll introduce you and we start.
Okay, no problem.
I think we're still recording, Matteo.
Yes.
Did you want to run it through the whole session?
Yeah, maybe, no? I don't know.
Yeah, that's fine, yeah.
That's a good, yeah, not to divide it in a lot of pieces.
If it's okay, can I request that my talk not be recorded?
Oh yeah, sure. Then in that case, let me stop it.